Yes, hello friends, welcome to the session. Continuation of chapter 7. I am discussing DC bridges. I already given some introduction. Then what are the different methods is used for measurement of resistance, I already explained. In that I am discussing in detail. First I started medium resistance measurement. In that medium resistance I already discussed one method, that is AV and VA method. Yes, ammeter, voltmeter and voltmeter ammeter method. I will say one more method with respect to medium resistance measurement, that is Wheatstone bridge. Okay. The second method for measurement of medium resistance is concentrate on Wheatstone bridge. Yes. Okay, this is 5-star concept for gate point of view, for other any competitive point of view. Sorry, concentrate on Wheatstone bridge. Small correction. Yes. Yes. I told already, among all the methods in the measurement of medium resistance, this is more accurate method. In the measurement of medium resistance, it's a more accurate method. Particularly I am talking about to measure the medium resistance. Okay. Now, what is the principle of Wheatstone bridge? Any DC bridge works on the principle of null deflection or zero deflection. The principle is null deflection. It works on the principle of null deflection or zero deflection principle. To operate the DC bridge, what is the source we are using? Supply is DC source. Any DC source is used as a supply. We know that in any bridge, to identify the balance condition, we can use the detectors. What type of detectors we can use in Wheatstone bridge? Detector is D-Arsenal galvanometer. D-Arsenal galvanometer is used as a detector, or it is also called PMMC. We are using D-Arsenal galvanometer. PMMC is used as a detector. Yes. Now tell me, what is the Wheatstone bridge circuit? It consists of 4 arms. Yes. Any bridge in general, any bridge consists of 4 arms. Then you draw this one. This is the bridge circuit. Parallelly note down, don't wait. Here we are using galvanometer to identify the balance condition. S. The supply is DC source. This is the battery voltage. Let this current is I1 and this current is I2 and this current is I3 and this one is I4. Clear? Let this is A, this is B, this is C, and this node is D. Let the current through the galvanometer is Ig. This is P, Q, R, S. This is variable resistance. Okay, where P comma Q is known ratio arm resistances. Correct this? Known ratio arm resistances. What is S here? Standard known variable resistance. Standard known variable resistance. Because of these are two ratio arms, that's why a Wheatstone bridge also called ratio arm bridge. Okay, the standard known variable resistance. What this R is unknown resistance. This is the resistance we want to find using Wheatstone bridge. R is unknown resistance. Clear? Okay. Let us assume that with these values of resistances, if this is P and this is Q and this is R and this arm is S, for these values of resistances, let us assume that bridge is balanced. If the resistance is beyond this, if that resistance values of any arm is changes beyond this, then we can say that bridge is unbalanced. But with this position, let us assume that bridge is under balance condition. Now I want to make some observation at balance conditions. What are the different conditions are satisfied in a Wheatstone bridge? Now you tell me, by seeing the bridge, how to say that bridge is balanced? Yes. If the galvanometer deflection is 0, then we can say that bridge is at a balance condition. Let at balance, the current through the galvanometer equal to 0. Yes. Let with these values of resistances, we are assuming that bridge is balanced. That means at this condition, the current to the galvanometer equal to 0 because bridge is at a balance. Can you tell me when the current through the galvanometer is 0? Yes. If this current equal to 0 means this potential and this potential is equal, then only we can say that current is 0. That means Ig equal to 0 means Vb equal to Vd. Ig equal to 0 means Vb equal to Vd. Clear? Now, when this Vb equal to Vd, I am telling that if Ig equal to 0 means this voltage and this voltage is equal. If this voltage and this voltage is equal, the potential difference is 0. When the potential difference is 0, there is no current from one node to another node. Clear? Now, what I am asking, this voltage and this voltage is equal means indirectly this voltage and this voltage drops are equal. Then only these two voltages are equal. That means if Vb equal to Vd means one condition is Vab equal to Vad, or we can define from this side also Vbc equal to Vdc. Yes, Vbc equal to Vdc. Then what is the meaning of this? Vab equal to Vad or Vbc equal to Vdc means what is the meaning of this? Yes, voltage across adjacent arms are equal. This is one condition at balance. Voltage across adjacent arms are equal. Adjacent arms are equal. But don't think like this, all these are the separate conditions. If this condition is satisfied means indirectly this condition is also satisfying. That is the meaning. These are not the different conditions. All are one condition only. If this condition is satisfied means indirectly this is also satisfied, this is also satisfied. Clear? Now VAB equal to VAD or VBC equal to VDC. What is VAB, you tell me? VAB is nothing but I1 into P. This is I1 into P is equal to, can you tell what is VAD? I2 into R. I2 into R. Or you also write like this. What is VBC? I3 into Q. I3 into Q. This is equal to, what is VDC? I4 into S. Yes, I4 into S. Clear? Now, tell me, at balance condition, I am telling that there is no current through the galvanometer. There is no current through the galvanometer means galvanometer at open circuit condition. If this is at open circuit condition at balance, then here there is no current means these two resistors are series and these two resistors are series. Yes. Now I am drawing the equivalent circuit at balance. Therefore at balance there is no current through the galvanometer means this resistance and this resistance is series. That P and Q is series. Then what about R and S? R and S is also series. I am drawing the equivalent circuit of the bridge at balance. Yes. This is P and this is Q and this is R and this is S. And there is no current through the galvanometer. That's why it acts as an open circuit. Okay. Now, actually this is the galvanometer. I am drawing this equivalent circuit at balance. Now, between this we are giving the supply voltage E. Clear? Now, what is this current from this one? This is I1. What this current we are assuming? I3. What this current we are assuming? I2. And this is I4. Yes. Tell me, if there is no current through the galvanometer means here there is no current. Here there is no current means these two currents are equal. Here there is no current means these two currents are equal. Shall you write like this? I1 equal to I3 equal to, I am writing expression for currents. I1 equal to I3 equal to, what the total voltage we are applying? E. Then what the resistance offered by this path? P plus Q. Shall you write like this? E by P plus Q. Yes. Similarly, you tell me what is I2 equal to I4 equal to? I2 equal to I4 equal to S E by R plus S. E by R plus S. The total voltage we are applying is E. Then what is this total resistance? R plus S. Now substitute I1 in this and I2 in this equation. Yes, substitute I1 and I2 here. Then if you substitute I1 and I2, then what you get, you tell me. That is EP by P plus Q, S, is equal to ER by R plus S. I am substituting I1 value here and I2 value here. S. Then you write like this now. P by P plus Q equal to R by R plus S. This is a condition at balance. P by, it is not a separate condition. We are deriving from these conditions only. That's why P plus Q equal to R by R plus S. Then if you cross multiply, what you can get, you tell me. PR plus PS equal to S. PR plus PS equal to PR plus QR. Then PR cancel. PS equal to QR. That means this is the condition at balance. At balance, if the bridge is at balance condition, PS equal to QR. What is the meaning of PS equal to QR? PS equal to QR. That is product of opposite resistances are equal. Product of, yes, product of opposite resistances are equal. This is, all these are calculated at balance only. Product of opposite resistances are equal. When the product of opposite resistance are equal, now from this, how to calculate unknown resistance? The unknown resistance are equal to S, P by Q into S. This is a measurement of unknown resistance by using which bridge? Wheatstone bridge. Clear? Now from this I am calculating R equal to P by Q into S. This is ratio arm resistance. This This is a measurement of unknown resistance by using Wheatstone bridge. It's a more accurate method. It is a more accurate method. Therefore, R equal to P by Q into S. Understood? What do you mean by PS equal to QR? PS equal to QR. Product of opposite resistances. All these are the conditions at which condition? Balance condition. Clear? Note down. Quick. Yes. Okay. Now, this is a measurement of unknown resistance by using Wheatstone bridge. We are measuring unknown resistance R equal to P by Q into S. One observation you remember here. In general, the bridges are broadly classified into two types. Not only DC and AC bridges. Either DC or AC bridge is broadly classified into two types. One is ratio arm bridge and another one is product arm bridge. The statements you remember with respect to ratio arm bridge and product arm bridge is, in any bridge, if the unknown and variable is adjacent, then it is called ratio arm bridge. In any bridge, if the unknown and variable is opposite, then it is called product arm bridge. Okay, but in every bridge you don't expect like this only. In every bridge you don't expect unknown and variable is adjacent. In some bridges may be adjacent, in some bridges may be opposite. But in the case of Wheatstone bridge, this unknown and variable is adjacent. That's why a Wheatstone bridge is also called ratio arm bridge. Understood or not? Why it is called ratio arm bridge means because of unknown and variable is adjacent. But in any bridge, if this unknown and variable is opposite, then it is nothing but a product arm bridge. That we'll see later on some examples of product arm bridge in the case of AC bridges. But this Wheatstone bridge is a ratio arm bridge. Okay. This is the analysis of Wheatstone bridge under balance condition. But point to remember, for commutative point of view, mainly gate point of view or any other commutative point of view, the analysis of Wheatstone bridge under unbalanced condition is very important. The analysis of Wheatstone bridge under unbalanced condition, that is also very important. Okay, write down. Put siding analysis of Wheatstone bridge under unbalanced condition. Put siding this one, analysis of Wheatstone bridge under unbalanced condition. Under unbalanced condition. Okay, that you concentrate. Let's assume that with these values of resistances, bridge is balanced. Yes, let the unknown resistance changes from R to R plus delta R. Actually, the unknown resistance is R, bridge is balanced. Let unknown resistance changes from R to R plus delta R. Because of change of resistance, then the bridge is unbalanced. Because of unbalanced, there exists a voltage across the galvanometer. Because of that voltage across the galvanometer, there is a current through galvanometer. That current must be sensed by the galvanometer. For example, for small change of resistance, there exists 1 microampere of current through the galvanometer. That 1 microampere also must be detected by galvanometer. Understood? If that 1 microampere is not detected by galvanometer, then galvanometer shows the zero deflection. Then we are thinking that still bridge is balanced. Then at that condition, if we measure the unknown resistance, then that is not accurate value. Clear? That's why if there is an unbalanced condition, because of unbalanced condition, whatever the galvanometer we are selecting, that galvanometer must be detect even small currents also. If you want galvanometer detect even small currents also, means whatever the galvanometer we are selecting, that galvanometer must be high sensitivity. This is very, very important statement. You remember. That means in the selection of galvanometer for any bridge, among all the characteristics, the first preference is given to the sensitivity. That's why the galvanometer, the detector which is having the high sensitivity, that detectors are more preferable. Why you give the preference to sensitivity means because of unbalanced condition, even small current is flowing, that must be detected. Then only you can measure the more accurate values. If it is not detect the unbalanced condition, under unbalanced condition we can measure unknown values, it gives the wrong readings. Clear? That's why the detector we are selecting for bridges, not only Wheatstone bridge, any bridges, the detector must be high sensitivity. That is the fundamental property is required. That is the basic property is required in the selection of the detectors or in the selection of the galvanometers. Okay. Let assume that unknown resistance changes. Let R changes from R to R plus delta R. Unknown resistance R changes from R to R plus delta R. Then bridge becomes unbalanced. Then bridge is unbalanced. Then bridge is unbalanced. This unbalanced condition, this unbalanced, parallelly note down, this unbalanced condition, yes, must be detected by galvanometer. Must be detected by galvanometer. Detected by galvanometer. For that detector must be high sensitivity. Detector, in a sense, for that galvanometer must be high sensitivity. Detector in the sense here galvanometer. Galvanometer must be high sensitivity. Yes. Must be high sensitivity. Yes. Due to unbalanced condition, due to unbalance, a voltage is induced across the galvanometer. A voltage is induced across the galvanometer, and current is exist through galvanometer, and current is passing through the galvanometer. Passing through galvanometer. Now, due to unbalance, a voltage is induced across the galvanometer and current is passing through galvanometer. Let the voltage induced across galvanometer is E, that E I want to calculate. The current through the galvanometer is IZ, that IZ I want to calculate. Okay, this is the analysis of Wheatstone bridge under unbalanced condition. Now what I am telling, the resistance is changing from R to R plus delta R. Because of change of resistance, bridge becomes unbalanced. Because of unbalance, there is a voltage across the galvanometer and there is a current through galvanometer. Now you want to calculate, that is what is the voltage across the galvanometer and what is the current through the galvanometer. To calculate this voltage across the galvanometer and current through the voltage across galvanometer and current through the galvanometer, then we can apply the Thevenin's theorem. Yes, concentrate, apply the Thevenin's theorem. To calculate this E and IZ, apply Thevenin's theorem. Listen please. Let us consider, this is the equivalent of bridge. This is P and this is Q. This is the ratio arm resistances. Now this is R plus delta R and this is S. The resistance is changing from R to R plus delta R and this is S. Because of this, there is a current through galvanometer. Let the galvanometer resistance is Rg, current through the galvanometer is Ig. And there is some voltage across the galvanometer. That voltage is VTH or E. I am taking as the Thevenin's voltage, or E I am considering. Let the supply voltage is E, capital E. Where small e is the voltage across the galvanometer under unbalanced condition. That is the Thevenin's voltage. First I want to calculate Thevenin's voltage. How to calculate Thevenin's voltage? VTH equal to E equal to. Any notation you follow. VTH equal to E equal to. Now I want to find this voltage. I want to find this voltage. VTH or E. Now what is the voltage across these two terminals? Let this is B and this is D. What is the voltage across these two terminal means? Because of change of this resistance only we are getting this voltage now. That's why you define from this one. You define voltage across from this one. Now I want this voltage means you find this voltage and this voltage. VD minus VB. Why I am defining from this one? Why not VB minus VB? Even you can define VB minus VD, but you can get negative sign only. But why I taken from VD itself means because change in resistance is in this arm. Wherever the resistance changes, from that you can define this VD minus VB. Now I want this voltage means I want voltage across this resistance. Voltage across this resistance means these two resistances are series. Once these two resistances are series means apply the voltage divider rule. Then what is VTH equal to E equal to voltage across this resistor I want. Total voltage is how much? E. That is E into R plus delta R by, these two are series. I am applying voltage divider rule for these two resistors by R plus delta R plus S minus. Now I want VB. Then we can find what is the voltage across this resistor. And these two also in series. How we can apply? E into P by P plus Q. Total voltage into that resistance by total resistance. This is according to voltage divider rule. Then what is the Thevenin's voltage? VTH equal to E equal to capital E into R plus delta R by R plus delta R plus S minus P by P plus Q. Okay, this is the exact value of induced voltage across the galvanometer. This is exact value. Yes, this is the exact value of induced voltage across the galvanometer. Then how to calculate Thevenin's resistance? We are applying Thevenin's theorem. Once we are applying Thevenin's theorem means you know the Thevenin's voltage and you also calculate Thevenin's resistance. Now calculation of RTH. Calculation of RTH. Tell me how to calculate RTH. Yes. Then to calculate RTH, Thevenin resistance, voltage source is short circuited. If voltage source is short circuited, what is the equivalent circuit? This is P and this is Q. This is P and this is Q, and this is R plus delta R, and this is S. Okay. Now voltage source is short circuited. This voltage source is short circuited. Now we are finding the Thevenin's resistance across these terminals. Okay. Whenever this is short circuited means these two are in parallel and these two are in parallel. Yes or no? If it is short circuited means these two are. We are calculating voltage across this one now. This circuit is redrawn like this. This is P and this is Q. This is P and Q, and this is R plus delta R, and this is S. Then this is short circuited, and these terminals bring into outside. Here we are calculating which resistance? RTH. Once we are calculating RTH means these two are in parallel. What is RTH equal to? P and Q in parallel plus R plus delta R is in parallel. R plus delta R and S is in parallel. This is in parallel and this is in parallel. This total is in series. That's why I'm writing RTH is like this. Okay, like this we can calculate VTH and this is RTH. These are the exact values. Once you know the VTH and RTH, then according to Thevenin's theorem, how we can write? According to Thevenin's theorem. Thevenin's theorem. Then how you can write? According to Thevenin's theorem, then Thevenin's voltage is connected in series with Thevenin's resistance, RTH. This is VTH is equal to E. And we are calculating current in galvanometer. Let the galvanometer resistance is RG. I am replacing with galvanometer by RG resistance. Let the current through the galvanometer is IZ. Then how to write IZ equal to? The current through the galvanometer IZ equal to VTH by RTH plus RG. That equal to E by RTH plus RG. Like this we can calculate Thevenin's voltage and current through the galvanometer. That is voltage across the galvanometer and current through the galvanometer. Like this we can analyze the Wheatstone bridge under what condition? Unbalanced condition. Now once you know the current through the galvanometer, what is the voltage across the galvanometer? Here I want to define three types of sensitivities. One is voltage sensitivity of galvanometer. That is a galvanometer voltage sensitivity. Another sensitivity is bridge sensitivity. Third one is a galvanometer current sensitivity. These three formulas are very important for competitive. Yes, quick note down. Yes. Now see here I want to define two types of sensitivities. Very important formulas here. Then we can take this is VTH and this is IC. Okay. This analysis of Wheatstone bridge under unbalanced conditions. Concentrate how you are calculating this VTH. Here resistance is changing. I want voltage across these two terminals. Then from this we can define what is the voltage across this one. Total voltage is E. E into R plus delta R by R plus delta R plus S, total resistance. Now I want this voltage, E into P by P plus Q. Across this series bands I am applying voltage divider rule. Across this series bands I am applying voltage divider rule. I calculating VD and VB, then subtracting. Then we are getting this formula. Clear? Yes. Here I want to define three types of sensitivity. The first one is galvanometer voltage sensitivity. Very important formulas, all these. Galvanometer voltage sensitivity. Voltage sensitivity. It is denoted by SV. Galvanometer voltage sensitivity is denoted by SV. The fundamental formula is deflection per change of voltage across the galvanometer. Is nothing but a voltage sensitivity of galvanometer. Now from this theta equal to SV into E, where theta is the deflection of the galvanometer, E is the voltage across the galvanometer. That means deflection per change of voltage across the galvanometer is nothing but a voltage sensitivity. Next, you define bridge sensitivity, that is Wheatstone bridge sensitivity. Bridge sensitivity. Bridge sensitivity. Yes. Then how to define bridge sensitivity? SB equal to deflection per unit change of resistance is nothing but a bridge sensitivity. Then what is theta equal to SV into E? E by delta R by R. This is the definition of bridge sensitivity. Yes. Next, galvanometer current sensitivity. Galvanometer current sensitivity. Galvanometer current sensitivity. Then how to write? SI equal to deflection per change of current through the galvanometer. Deflection per change of current through the galvanometer. Okay, these three definitions important. Clear? Okay, this is galvanometer voltage sensitivity, bridge sensitivity, galvanometer current sensitivity. Now from this I want to explain some important observations that is also important for competitive point of view. Yes, we know that you write as a note, we know that what is voltage across the galvanometer? VTH equal to E into R plus delta R by R plus delta R plus S minus P by P plus Q. This is exact formula for voltage across the galvanometer. That for approximate analysis, then replace P by P plus Q equal to R by R plus S. This formula already given in the this condition I derived under the assumption of balance condition. But this condition I am applying for in this case P by P plus Q equal to R by R plus S. Then what is VTH equal to E equal to capital E? Capital E is the supply voltage, okay, battery voltage. Is R plus delta R by R plus delta R plus S. What is P by P plus Q? R by R plus S. Now This we simplify by simplifying and neglecting higher order terms. By simplifying, yes, and neglecting higher order terms. And neglecting higher order terms. Higher order terms. Then what is VTH equal to? E equal to S. We can get directly, I am writing ES into delta R by R plus S whole square. This is one more formula for voltage across the galvanometer. But this is not exact, this is approximate. VTH equal to E equal to ES into delta R by R plus S whole square. But now we know that what is bridge sensitivity SB equal to theta by delta R by R. Change of deflection per unit change of resistance in a bridge, that is nothing but bridge sensitivity. This you also write like this now, SV into E by delta R by R. I want to get one standard formula, that's why I am doing analysis like this. SV into what is E? ES into delta R by R plus S whole square into delta R by R. This delta R cancel. Is correct? Now from this you tell me what the bridge sensitivity SB equal to SV into ER by R plus S whole square. Then you simplify this, bridge sensitivity SB equal to, this is SV into E by R square plus S square plus 2RS by, I am bringing this RS, R is, this is SV into ERS by RS you can write. This RS I am bringing into denominator. Then what you can write? SB equal to SV into E by, we simplify this, R by S plus S by R plus 2. R by S plus S by R plus 2. Then this is one more formula for bridge sensitivity. SB equal to SV into E by R by S plus S by R plus 2. When this value is maximum, if R by S equal to 1, then what about S by R is also 1. If R by S equal to 1, then S by R is also 1. Then SB equal to SB max. The bridge sensitivity is maximum. Therefore, maximum bridge sensitivity equal to maximum bridge sensitivity. The maximum value of bridge sensitivity. SB max equal to, then SV into E by R by S is 1. If R by S is 1, S by R is also 1. Then what is the maximum value of bridge sensitivity? SV into E by 4, 5-star formula. What is the maximum value of bridge sensitivity in Wheatstone bridge? SV into E by 4. That formula also you remember. Yes? If this value is maximum if only R by S equal to 1. Sir, is it possible only for R by S? I will substitute R by S equal to 0.5. I will substitute R by S equal to 2. We never get greater than this value. This is only the maximum value. You substitute any another value, we can get this bridge sensitivity less than this one only. That's why for R by S value equal to 1 only, this we can get the maximum value. If R by S equal to 1 means indirectly what about S by R is also 1. That's why the maximum bridge sensitivity equal to SV into E by 4. This formula also you remember. Yes, quick, note down. Over? Yes. One more relation I want to give here. Yes, we know this. What the galvanometer current sensitivity? The current sensitivity of galvanometer, you write as a one more note this. The current sensitivity of galvanometer SI equal to theta by IC. We know that theta by what is Iz? E by RTH plus RG. This formula already given. Iz is E by RTH plus RG. Then from this, what is SI equal to theta by E into RTH plus RG. Okay. What is S theta equal to SV into E by E into RTH plus RG. I am writing one more standard relation. E cancel. Then what is SV equal to SI by RTH plus RG. RTH Thevenin's resistance, RG is the galvanometer resistance. This is the relation between current sensitivity and voltage sensitivity. In a Wheatstone bridge, we may expect by giving the current sensitivity, we may expect voltage sensitivity. By giving voltage sensitivity, we may expect current sensitivity. Then this relation is also very important. Still now in any competitive exam, based on this, no question, but in future compulsory we can expect. But this based on this already question is there in competitive exam, that you concentrate. That means in a Wheatstone bridge, mainly for gate and IS point of view, mainly you concentrate on how to calculate voltage induced across the galvanometer under unbalanced condition, how to calculate current to the galvanometer, what is the maximum value of bridge sensitivity, and what is the relation between voltage sensitivity and current sensitivity, and what is the definition of three sensitivities: galvanometer voltage sensitivity, bridge sensitivity, and galvanometer current sensitivity. This about in detail analysis of Wheatstone bridge. Understand? Yes. Note down quick. Okay. This analysis with respect to Wheatstone bridge, this is one of the method of measurement of medium resistance. At starting I given AV and VA method, and this method is Wheatstone bridge method. Okay. Can you tell me what is the applications of Wheatstone bridge? Where we can use this Wheatstone bridge? I want to explain one or two applications. We write this theory questions only for application point of view. Concentrate on what are the applications of Wheatstone bridge. Yes. One of the application of Wheatstone bridge is these are used in firing alarms. Used in firing alarms. Wheatstone bridges are used in firing alarms. If any firing problems are there, then because of temperature effect, the resistance will be changes, bridge is unbalanced, there is a current through galvanometer, then it gives the alarm sound. Then in firing alarms we can use, in smoke detectors also we can use this Wheatstone bridge. Smoke detectors. Smoke detectors. In smoke detectors we can use this Wheatstone bridge. And signal conditioning circuit of transducers. Signal conditioning circuits. That means in a transducer, if you want to convert change of resistance into voltage or current, then we can use Wheatstone bridge. Signal conditioning circuits of transducers. Signal conditioning circuit of transducers. You know what is the function of signal conditioning circuit in transducers? That signal conditioning circuit will convert change of parameter into either voltage or current. In that application also we can use this Wheatstone bridge. One of the application is in the case of what type of transducer means in strain gauge. In strain gauge we can use the Wheatstone bridge. Next, We also use uh, fault location in underground cables. Fault location in underground cables. Fault location in underground cables. Underground cables. Using Murray loop test. Murray loop test and Warley loop test. In these tests also we can use this Wheatstone bridge. These are the main applications of Wheatstone bridge. Can you give what is the limitations of Wheatstone bridge? Limitations of Wheatstone bridge. Wheatstone bridge. What are the limitations of Wheatstone bridge is? The point to remember, it is used only for measurement of medium resistance. It is not used for measurement of low resistance. Wheatstone, one of the limitation is Wheatstone bridge is not used for measurement of low resistance. Why it is not used for measurement of low resistance means because it cannot eliminate effect of lead wire or connecting wire resistance. I told already, if in the measurement of low resistance, if the connecting wire resistance is added, then it gives a serious error. That is a problem. That's why by using Wheatstone bridge directly we cannot eliminate the effect of lead wire or connecting wire resistance. That's the reason why this bridge is not used for measurement of low resistance. The another limitation is Wheatstone bridge is not used for measurement of high resistance also. Why the Wheatstone bridge is not used for measurement of high resistance means, for example, let us consider this is one Wheatstone bridge. Why this bridge is not used for measurement of high resistance? Okay, this is Wheatstone bridge. Okay, now this here we are connecting very high resistance. Very high resistance we are connecting. Let us assume that. If you connect high resistance, whatever the source we are using, that source is not sufficient to drive the current through high resistance. When the source is not sufficient to drive the current through high resistance, then balance of bridge becomes very difficult. Balance of bridge is very difficult. That's the reason why this bridge is not used for measurement of high resistance. Then we have one doubt here. Sir, if source is not sufficient to drive the current through high resistance, replace low voltage source by high voltage source, then we can use for high resistance. Yes, that modification is also there. That means in a Wheatstone bridge, if the low voltage source is replaced by high voltage source, then that bridge is used for measurement of high resistance. That bridge is called mega ohm bridge. That's why a mega ohm bridge is the modification of Wheatstone bridge only. I told already, mega ohm bridge is the one of the method of measurement of high resistance. That's why mega ohm bridge is derived from the Wheatstone bridge only. In a Wheatstone bridge, if the low voltage source is replaced by high voltage source, then it is used for measurement of high resistance. That is called mega ohm bridge. In detail later on I will explain mega ohm bridge. And this bridge is not used for measurement of low resistance because it cannot eliminate the effect of lead wire or connecting wire resistance. Now we can modify this bridge to eliminate effect of lead wire or connecting wire resistance. That bridge is nothing but a Kelvin double bridge. That's why Kelvin double bridge also derived from which bridge? Wheatstone bridge only. Okay, that remaining what is mega ohm bridge, what is the Kelvin double bridge, that is separate concept that I will explain in the measurement of high resistance and low resistance measurement. Up to this, with respect to Wheatstone bridge, these are the two main limitations. It is not used for measurement of low resistance. You note down this one. It is not used for measurement of low resistance because it cannot eliminate lead wire or connecting wire resistance. Second statement you note down. It is not used for measurement of high resistance because balance of bridge is very difficult. Balance of bridge is very difficult. Yes. And source is not sufficient to drive the current through high resistance. Clear? Okay, this about in detail what exactly Wheatstone bridge. Okay. Still in the measurement of medium resistance, still two methods are there. One is direct deflection method. Sorry, not direct deflection method. Sorry. One method is substitution method. The another method is ohm meter. Okay. With this, medium resistance will be complete. In the next session, we will continue with the substitution method and make ohm meter. Then after that I will start the measurement of high resistance. Okay, clear? Concentrate. Thank you.